That cover all the chemical reactions at the same time. And since there are only 3 types, but there are different ways that we solve these. So let me talk about it here. All right, so the different types of reactions that we have are the metathesis. One type, these are just ion combinations. And then, one type is the double replacement. Etc. I mean, you can figure out any way that you can mix and match ions that would work an ion combination. The second type we did was acid-base. And we have 2 major types here. We do Bronsted and Lewis. Lewis is going to come later. But Bronsted is what we did. Bronsted is where we have the proton transfer. The hydrogen ion transfer. Lewis is a little different, the way we define what an acid is and what a base is. And then 3 is redox. For redox, they're the element plus element, so reaction of the elements to form compounds. Here you just look at what the common charges are. So metals tend to form cations, non-metals tend to form anions. So we could figure it out. And some metals form variable charge cations. What forms a variable charge cation? We just look the redox chart to try to figure out, or try to take a guess at what the most stable charge is. This can be reversed. A compound can be broken down into elements via chemical means. And so going forward, it's called the combination. Going reverse is called decomposition. That's okay, but Krakalici calls other types of reactions combination as well. Acid-base and these, so all these can be thought of as combination reactions. The way looking at the ion combination, etc. So we have this, and then we had single replacement. Which we looked at the pattern, the A plus BX pattern. Yields AX plus B. And then we also have combustion reactions. For combustion reactions, we're going to take a hydrocarbon, so it's going to be a CH or CHO. A hydrocarbon is just a compound of carbon and hydrogen. The CHO could be a sugar, it could be an alcohol, it could be a lot of different organic species, ethers, etc. But if we take a CH or a CHO, then we just combine it with O2, so we get CH, maybe O in there, plus O2 yields CO2 and water. And then we balance it. So the products are going to be the same, whether there's oxygen or not present. That's combustion. And then we have the chart method. The chart method is where you look, for the oxidizers and reducers. You do the inventory, and then the strongest react. But we have to determine driving force. There may not be, even when you pick the strongest, they might not be strong enough to react. So that's a chart method. We spent some time looking at that. Well, there's one more method. This is up now. skeleton redox. Skeleton redox here, the goal is not to predict the products. You know, all these other ones we predict the products. The goal is just to balance, just to complete and balance. We don't predict the products. You know, chemical reactions are actually quite complicated. They're quite complicated in the sense that, you know, for example, I know I can make soot. I know I can make carbon monoxide from the flame, you know, but let's say I wanted 50% carbon monoxide, 50% soot. You know, what conditions are required to get that? Or let's say I don't want any carbon monoxide, I don't want any soot, so I want 0% carbon monoxide, 0% soot, 100% CO2. What conditions can achieve that? And so there are different conditions here. Those conditions are called stoichiometry. You know, stoichiometry are the amounts, you know, not just the amounts, but also temperature, pressures. A whole bunch of variables can affect what the products are. And so here, many variables can affect what products are obtained. You know, the common ones are concentration, you know, high concentration, low concentration. You know, pressures. Pressure has the same effect kind of as concentration. High pressures means usually highly concentrated, etc. Temperature is a big one, you know, low temperature versus high temperature, etc. So if we start playing with all these variables, then we don't know exactly what the product will come out as. You know, it's hard to predict theoretically, you know, what you're going to form. Although people want to do this, they want to be able to predict under what conditions am I going to get, you know, the desired products. And so you have two approaches to this. One approach, you have the theoreticians trying to predict it using the theory of chemistry, which is quantum mechanics. On the other hand, you have the experimental chemists, the synthetic chemists, and they just mix it and match it. Although they aren't completely separate, because if you're an experimental chemist, you make adjustments. So some of the experimental chemists, what they'll do is they'll do a run of 1,000 reactions to see, you know, what the optimum conditions are. So for example, they're trying to develop a new catalyst. And so they kind of have an idea of their target based on some theoretical calculations. But what they'll do is they'll get a microreactor. A microreactor, they can do, let's say, 1,000 different variations on a single plate, and then just make micro quantities of that, and then figure out which one works best. The same thing in drug design. The same, you know, in drug design, you either just do a shotgun approach, you try a whole bunch of variations of the same thing, or you try to target it to one, you know, based on theory, this is the one that should work best. And so this is more of the shotgun approach. You just kind of mix it and see what happens. You know, the theory is kind of complicated, so we just mix it and see what forms. And so this is called the skeleton redox method. And the skeleton redox method, like nitrate can form a whole bunch of different oxides of nitrogen. Typically, you know, if we have something like nitrate, or we're burning nitrogen, or we're doing something, then we typically form NOx. NOx stands for NOx. And we don't know how many oxygens are on there. It could be one oxygen, it could be two oxygens, like nitrogen dioxide. It could be half an oxygen, like nitrous oxide. And so usually what happens is you end up with a mixture like this. Although we don't want too much carbon monoxide from our flame. If we're getting too much carbon monoxide, you know, the maximum allowable level of carbon monoxide is 10 ppm. So if we exceed 10 ppm, then period that exceeds the OSHA limits for that, so we got to detect that. Well, the same thing here, well, what's the major product? Well, it depends, it could be NO. NO is pretty stable, it could be others. NO's I shouldn't say pretty stable, it's still pretty reactive. And so in a typical skeleton redox, we have a question like this. If the permanganate ion is a strong oxidizing agent that oxidizes chloride ion to chlorine in an acidic solution, manganese ends up as a monatomic manganese 2 ion. Write the net ionic equation for the redox reaction. So here they tell us, what's going to happen. We just have to complete and balance it. And so, under these conditions, permanganate. Actually, I need the towel erasers. So under these conditions, permanganate reacts with chloride ion. So this is what we have here. We have permanganate reacts with chloride ion. And then they tell us that the permanganate goes to manganese 2 plus, and the chloride goes to chlorine. And so they show, the permanganate ends up here, the chloride ends up here, chlorine. Well, this one we could have predicted, because this one, if we use the chart method, we would have gotten the same thing. But if we adjust the conditions, we might not have. We might have gotten something else, by adjusting the conditions. And so the chart method assumes a certain set of conditions. Do you know what the conditions the chart method assumes? Well, if you take a look at the chart here, there's a little footnote on the chart. I'm not going to bring up the chart in our book, but the same goes for our chart too, the one I have posted. You see this footnote here? What does it say? It says that. Yeah, these are for neutral aqueous. All other E naught values for 1 molar. Okay, so we're dealing with 1 molar ion concentrations at 1 atmosphere, and this chart's for 25 degrees C. So the restrictions on the chart method are you've got to operate at 25 degrees C with 1 molar, 1 atmosphere, or 1 bar for the gases. If we vary those, then that's going to change things as well. And so, under normal conditions, this is what I would have formed under the chart method. But we're going to use the skeleton redox method to solve this problem, because this show. Now, if I were given this problem, I wouldn't have used. I would have just got it. So here we have our skeleton equation, and then what we do is we split it up into half reactions. So this would be called a half reaction here, and this would be another half reaction here. And so we're going to separate the 2 half reactions. So the first half reaction is permanganate goes to Mn2 plus. Okay, then we work each half reaction individually. So let's start just with the first half reaction here. Now, actually, this is they started on the other one. It doesn't matter. I'll just go through it. And so the way we do it is we balance all elements other than oxygen and hydrogen first. And so when we balance all elements, we have 1 manganese on the left and 1 manganese on the right. And so we're balanced. We don't have to do anything. Okay, then we balance the oxygens next. And so these instructions are here, are written. So balance all elements other than H and O. And so it worked out, it's balanced here. Okay, the other half reaction, let's take a look. The other half reaction is chloride goes to chlorine. Now here, it's not balanced because on the left I have one chlorine atom. On the right I have two chlorine atoms. One chlorine atom is the ion, and two chlorine atoms is the element. And so here it's not balanced. The way we balance this is we change the coefficient. So we need to put a 2 in front of here. So we balance all elements other than H and O by changing the coefficient. The coefficient is the number in front. We never change the subscript, and so it would never be like this, chloride with a sub 2 there. That would be wrong. So this would be a some other species. So we have 2 chlorides there. And so we change the coefficient. Okay, the next is we balance the oxygens. So this is one. Actually, no, we separate into the half reactions. But I don't need the step numbers here. And so next, balance the oxygens. But the way we balance it is very strange. And so over on the left, how many oxygens do we have? 4 oxygens. On the right, we have none. And so we don't just add O. We balance the oxygens by adding H2O. And so here I need 4 oxygens, but I'm going to do this by adding 4 H2Os. So here, now I'm going to have 4 oxygens on both sides here. Over here, when I look at the second half reaction here, I don't have to worry about it because there are no oxygens on both sides, so I don't do anything. There, it's already balanced. All right, then we balance the hydrogens. Balance the H. Here we balance the H by adding H plus. This side is deficient. And so when I look over here, over on the left I have no H's. Over on the right I have how many H's? 8. And so what I'm going to do is I'm just going to throw in 8 H pluses here. That should do it. So plus 8 H pluses. Over here, I don't have to worry about it because there are no H's on both sides. So I'm set. All right, then there's the last step in this, which is balance the charge. So balance charge, but we do this by adding electrons. And so what we have to do is we have to sum total the charge on the left. So permanganate has a -1 charge, and then we're adding 8 H pluses. And so the total charge on the left is the permanganate plus the 8 H pluses is going to be +7. Okay, on the right I have 2 plus from the manganese, and then the 4 H2Os are neutral. So the 4 H2Os are neutral, that gives me a total charge of +2. And so I have to make +7 and +2 the same by adding electrons. Electrons are negatively charged, and so how many electrons do I need to add?
5.
Yeah, I need to add 5 electrons on the left. That works. Over here, let's take a look at the charge. What's the charge on the left?
100.
Well, then I have 2. So it's going to be, and then the right? Neutral. And so I need to add 2 electrons here on the left. So now I'm done. I just add everything up. And so on the left I got permanganate plus 8H plus 5 electrons. This is going to yield manganese 2 plus 4 water. when I look at this, I think what a waste of time this was for me. Why? Because, show you. Why? Because it's already here. You know, when permanganate goes to manganese 2 plus, then we need 8 H pluses and 5 electrons. We're going to form Mn2 plus for water. And so this one I didn't need to do the skeleton. I could have just copied it off the chart. So the same thing with the second one. This is 2 chlorides. Goes to chlorine plus 2 electrons. Well, that's here. 2 chlorides goes to chlorine plus 2 electrons. So I didn't need to do that one either. So I could have saved some time. Just wrote them straight. So these are the 2 half reactions. To get the net reaction, we have to add these up. This one is called the oxidation or reduction half reaction. Now, when we look at this, we have to remember oil rig. Oil rig. Oil, OIL. Stands for oxidation is loss. And then rig is reduction is gain. Well, we're talking about our electrons. And so is this losing or gaining electrons, this first one? This is gaining. So what we do is we call this the reduction half reaction. And then this one is the loss. And so this is the oxidation half reaction. And then when we combine it, we'll get the net redox reaction, reduction oxidation. Now, chloride was oxidized. Chloride was oxidized is what we say. By whom? Who oxidized chloride? Did chloride oxidize itself? No, chloride did not oxidize itself. Something oxidized chloride, and that something that oxidized chloride is who took the electrons from chloride? Permanganate did. And so what we do is we call this permanganate and H plus. This is called the oxidizing agent. Chloride is called the reducing agent. And so they get all this terminology in redox gets confusing because the oxidizing agent is reduced. The reducing agent is oxidized. And so people get that mixed up all the time. So what you have to do is you go through it over and over until it clicks. And once it clicks, then you figure it out. Well, when we have the half reactions like this, the other thing we notice is this is the conjugate reducing agent. And this would be the conjugate oxidizing agent. So they occur in conjugate pairs here. And so what we're going to do is we're going to combine these. In order to combine these, I'm going to have to, I got 5 electrons, but only 2 electrons here, so electrons are mismatched. And so I'm going to multiply the top one by 2. I'm going to multiply the bottom one by 5. So we got 10 electrons gain, 10 electrons lost, so the electrons match. So make sure the electrons gained equals electrons lost. Electrons gained equals electrons lost. That's very important. Yeah. And so this is why we're multiplying it here, like this. And so that's going to give us 2 permanganates plus 16 H plus 10 electrons from the top. Then we got to add the bottom reactants plus 10 chlorides. Okay, then we'll go to the top here. 2 manganese, 2 plus is a product, plus 8 H2O. There. Then to the bottom, gives us plus 5 chlorines, plus 10 electrons. And so what we have to have is this, the electrons lost equals electrons gained. So electrons must cancel out in a redox reaction. Okay, then we look at if we can simplify anything else. Is there something else? No, that looks to be about it. And so what we're going to get is 2 permanganates plus 16H plus 10 chlorides yields 2 manganese 2 plus 8 H2O plus 5 chlorine. So there is a driving force present, otherwise we wouldn't have gotten, we wouldn't have gotten this. So this is an additional thing you could do. That's not necessary. This is going to be a stronger oxidizing agent. The reverse here, than chlorine, this is going to be our weaker oxidizing agent. This is going to be a stronger reducing agent. This is going to be a weaker reducing agent. And so this says permanganate and acid, H plus, is a stronger oxidizer than chlorine. Does that make sense here? Permanganate is a stronger oxidizer than chlorine. That's correct. Now, I'll put a little asterisk here because if we use the chart method, note, chart method, let's say we had permanganate, acid, and chloride present. There would also be water present here. Now, the chart method would have made a different prediction. That has to do with chloride versus water. Which of these is a better reducing agent? Chloride or water? Okay, when we look at the chart, what is the best reducing agent on the chart? The best reducing agent is lithium. So as we go up, we hit water here first, which goes to oxygen, and then we hit chloride, which goes to chlorine. So which is better? Water. Water is better. And so which of these is a better reducing agent? H2O. If H2O is a better reducing agent, then why is chloride oxidized, not water? Now here comes a confusing thing. Water, according to the chart, now I told you there are variables. There are other variables that impact what products we form. This is one of them. One of the variables is that it's much easier to strip electrons from chloride than it is from water. When you strip electrons from chloride, you're just taking an electron off of an atom here. So you just plug an electron. Probably the electron farthest away from the nucleus. So if an oxidizer comes in, just plugs an electron off there. So you plug an electron off, and then it forms a bond with chlorine. When you plug electrons off water, you got to strip them off the oxygen. In other words, when we strip it off water, you got to break the hydrogen-oxygen bonds, and then you got to pull the electrons off of the oxygen, which is -2 here, goes to 0 here. You're going to pull it. And so we call this mechanistically. Mechanistically, stripping electrons off water is much more difficult than stripping electrons off chloride. And so this is it. This is it. You know, sometimes some things cost less money, but involve more hassle, you know? And so let's say this one costs less money, but it's much more difficult, much more of a hassle to do, versus this one, which costs more money, but is a lot easier. And so it depends on your wallet. If you have plenty of money, and you could afford it, maybe you'll take the easier route, you know, to save you a little bit of work, right? Versus this one, you know, well, you want to save more money, then you're going to have to make more compromises, more sacrifices. And so in nature can afford both. Since nature could afford both, it's going to take the easiest route. The easiest route is chloride. So this is the only exception in the chart method, according to chart. But this is the only exception that we should know. When it comes to oxidizing chloride versus water, chloride versus water, water should win when it comes to oxidizing as an RA. But chloride wins. We call this kinetics. Due to other factors. I'll just leave it at other factors. We don't want to get too deep with this. And so this is the only thing you have to keep in mind. When we have chloride versus water, chloride's going to win. And so this gives us a way. So rather than forming oxygen gas, we form chlorine gas. Otherwise, we would have predicted we should have formed oxygen gas because we oxidize water, that's what we'll get. But we end up with chlorine gas. The other factors are what I talked about, you know, about mechanistically it's easier to oxidize chloride. All right, not everything is going to be on the chart. You know, some things are going to be off the chart. So let me give you an example of that. For combustion, you know, for combustion, do we always form just CO2 and water? You know, in combustion, can you sometimes can you form carbon monoxide? Can you form soot? Yeah. So we make the assumption that for combustion, we're always going to go to complete combustion. So we always form CO2 and water. But for a skeleton, we don't have to do that. So for example, if we burn ethanol, C2H5OH. When we burn ethanol, what should it form? It should form carbon dioxide and water. Then, did I tell you about the Santa Barbara wine I bought at the dollar store? Yeah. Well, you know what happened was some oxygen got into the headspace there. And so normally when we react ethanol with oxygen, we should go all the way to CO2 and water, but just a tiny bit of oxygen got in there. The tiny bit of oxygen just partially oxidized my ethanol. It didn't completely oxidize it, because if it completely oxidized it, it would have went all the way to CO2 and water. So it turned out the conditions were just right in that bottle of wine to convert my ethanol into not CO2, but this. You know what that is? Acetic acid. And so the conditions were mild that it just partially oxidized. We call this partial oxidation. It partially oxidized my ethanol to acetic acid or vinegar. So it converted the wine into vinegar, basically. Okay, then, well, I want to know what happened. So what I'm going to do is, this is what we call skeleton redox. This I know happened because when I tasted the wine, it tasted like vinegar, right? And so now I got to figure out, well, what are all the other details of what happened? So here, I know the ethanol was converted into acetic acid. Acetic acid, there are two ways that the formula for acetic acid is written: HC2H3O2 or CH3COOH. Those are the two common ways. And so here's one half reaction. But what happened to the O2? I don't know what happened to the O2. But, you know, I don't care, because oxygen and hydrogen you don't have to care about, because those will balance in the end. And so what we're going to do is we're going to split this up into two half reactions here. Well, the first one is here, ethanol to acetic acid. Is that on my chart? Redox chart? No, it's not. And so under these particular conditions, this is what I got. And so let's give it a shot. Actually, rather than me giving a shot, why don't you guys give it a shot and tell me what happened here?